My name is Arun Gupta. I am the VP and the General Manager for Open Ecosystem Team at Intel. You can learn all about us at open.intel.com or also listen to our wonderful podcast that is also on that page as well. Today, I'm really excited to have two speakers with me, Ravi and Badri. Hey, Ravi and Badri.
Hey,
All right, you want to introduce yourself?
sure. Yeah, I think it's great to be back on your show, Arun. So I'm Ravi. I'm a senior PE in the Xeon Software Group, and I drive software engagements with AWS. And yeah, so over to you, Badri, who's my colleague.
Hi, my name is Hari Pulavarthi. I am a senior technical lead for the AWS software group. Closely work with Ravi. We focus on optimizing AWS software for the Intel hardware.
Beautiful. And so today we are going to be talking about all the innovations that we have done. Well, one of the innovations that we have done for m7i, which is the recently launched fourth generation based Xeon based instances in AWS. And so let's get started. Why don't we see some slides?
It sounds good. Let me start sharing. Give me a second here. All right. Okay, so let's jump right in. We already saw the title, the most important slide, but I'll get past this legal notice thing. Okay.
But actually, go back to the slide title because I don't think people realize what the title is about. So
Okay. Sorry, let me do that and let me pause for a second because it tends to buffer sometimes, I guess.
yeah.
So yeah, we're talking about the common runtime libraries, or CRT as AWS refers to it, and some of the optimizations that we have done to those libraries that will show up with extensive performance improvements on the latest generation of instances, the M7i, C7i, R7iZ, and the upcoming ones that are all based on the Intel Xeon 4th Gen processor. That's
Beautiful.
really the goal. Yeah.
And when we last time talked, that was the launch of M7i. What has changed since then? The other instances have been launched. What is sort of the landscape like?
Yeah, so the last time we talked, yeah, I mean, I think M7i had launched and C7i had just launched. We also have R7iZ, and I think there's more coming down the line very quickly. We should expect to see the R7i and MetalLab as well, I believe. So we also have been working with many customers that have started adopting these instances. And we've also been working with some of the AWS services so that they can offer these instances as options for especially for the PaaS offerings where the customer can choose what the underlying instance can be. So we're seeing the momentum growing, and there's a lot of adoption that I'm sure is happening.
Beautiful. Seven means the seventh generation of Intel in AWS, but that is based upon the fourth gen Xeon that we have within Intel.
That's right.
Got it. Perfect. Okay, let's get going.
Okay. So let's jump into this. Yeah. So this is a a good context setting slide. I won't talk about all of these things. So those that are interested, you can go over the details. There are some reference links at the bottom, but the one in the middle, right, the cloud security piece, is the one that's most important for today's topic. Security has a lot of different things that are associated with it. Here we're focusing on encryption, and adoption of that, obviously, especially in the cloud, has exploded, right? And it'll continue to grow and become pervasive, right? But it's encryption not only during transit, meaning encrypted connections, but it's also encryption at rest, and then also encryption of data during use. But in general, there's a box in the bottom, which are all the boxes at the bottom are talking about the new hardware capabilities that are coming up, right? And these are industry trends, not just Intel. But taking advantage of these hardware capabilities can make the last challenge listed, the developer productivity and developer skill set, it can make it harder. So what we're talking about here really is about how you can improve cloud security, adopt encryption for multiple use cases using the specialized ISAs, right, which are one of the hardware capabilities here, and how we can simplify that. And that's the approach we're using, and that's what we're that's why we're sharing this overview.
So you said specialized hardware ISAs. What are those?
Okay, so let me go into this a little bit and then come back to prior slides. This is a bit of a, well, too much content maybe on a slide. But so we have, at the bottom, I've listed some of the hardware instructions that were introduced in the prior generation. So they're in the Intel 3rd Gen Xeon, but it's available on the m6i, c6i, r6i family. And they've been significantly improved in the latest gen, so on the m7i, c7i. So all software that takes advantage of these hardware instructions just operate faster, right? And I won't go through all of the details here, but as you can see, hopefully it's readable. Uh, all of these hardware instructions are specifically meant to improve the ciphers and algorithms used for the various encryption modes, right? And the diagram at the top, that's really what it's showing, that if you're thinking of microservices implementation or most cloud native design patterns, you have some kind of API gateway. There's a load balancer that distributes the connections that are coming in. There might even be an application firewall. All of these are proxies and so on. All of these deal with millions of connections per second, and they're all encrypted. So there's encryption decryption, there's key pairs for signing and verification, there's encrypted communication through gRPC or service mesh. You have encryption that's involved in reading and writing data on storage clusters, and also hashing, request signing, uh, data compression, decompression operations on in the computation side of it as well. So all of these areas are dealing with operations that can be accelerated with these hardware instructions. That's the context for this.
So these hardware instructions are the new instructions that are available on the Xeon. Some were introduced in 3rd generation, now introduced in 4th generation. So the idea is to be able to leverage that ISA or instruction sets to be more effective user of a software on top of that hardware.
That's correct.
Gotcha. And I think the point that you mentioned earlier is when customers are building applications, they have a stack. Now that could be at a virtualization, like a hardware level, operating system, virtualization, actual application, Java, whatever, microservices, Kubernetes, all of this. In that entire stack, encryption is one part of it, but it's a very critical part of it because that's what allows you to do security at rest, in transit, in runtime. And so we are focusing on that element.
Yes, and I know it's actually so surprising the extent to which we do see that encryption is involved, and in many cases it's transparent. So, for example, if you have a Java-based application and anything later than a 11.0.18 version of OpenJDK, as listed here, you're getting the advantage of these without necessarily needing to do anything specific for it, right? And obviously, OpenJDK 17 has even more optimizations in there. So if you profile it, use a GFR, or the flight recorder, or any profiling tool, you'll actually see that OpenJDK and the JVM is actually taking advantage of these hardware instructions. So these are things that are the support has started getting added into the open source ecosystem for some time. And what happens in the latest generation, which is each of these operations gets completed in fewer cycles. So there's additional performance improvement.
And that's the beauty of that's why Intel contributes to open ecosystem, because we don't want to be in customers' way. We want to be completely out of customers' way, enable it for them, empower them, and do it in the most optimal and efficient manner in a very upstream compatible way, and make it available in downstream. So for example, as you mentioned about Java 17, we do the contributions to upstream. Those are all available in downstream distribution like Oracle JDK, Amazon Corretto, Eclipse Adaptium, and customer by default get it. And so if they're using the latest upstream downstream software and the latest Intel Xeon, like on a cloud provider of your choice, boom, you just get the magic automatically.
That's exactly right. And one last thing I'll mention from this is besides the hardware instructions and the software enabling to take advantage of them, uh, the Intel implementations, the QAT engine mechanism, there are some additional innovations that were introduced there, which can further enhance the throughput that you can achieve, right? Because the hardware instructions can process multiple uh, operations at the same time. So that's also something that's more in the software innovation area, but we'll talk more about that going forward. But maybe I'll switch back to this. And Badri, do you want to give a quick overview of the common runtime libraries?
Sure. So the AWS common runtime libraries are the set of the base libraries that are provided by AWS. So their goal is to provide a simplified version of these standard libraries that are used by all the services. And each package provides good performance and also provides a minimum footprint, because if I'm trying to build a service, I don't need to worry about what version of common libraries I should get, what like version of HTTP I should get, what slot version of S3 libraries I get. So AWS provides a common runtime libraries that are optimized for running on the AWS instances. So AWS handpicked most commonly used libraries, and they took the implementation from mostly open source projects, but they stripped down the versions of those libraries such a way that they know what exactly is they're maintaining, and they're getting on the AWS hardware. So if you look on the left, there are, I guess, about handful, about 15 or 20. Each one has specific functionality, provides specific functionality, and most commonly used ones were the AWS Common, the compression libraries, and then authentication libraries, and then crypto libraries, and then S3 libraries and checksum libraries. So these are the libraries that are provides the basic common functionalities or the building blocks to build a service.
That's wonderful. So, as AWS customers are building applications, they are leveraging these libraries as part of the application, because then they're abstracted. This is true customer obsession. They're just using the CRTs, they're getting the functionality. What's the underlying mechanism? How is it implemented on the underlying hardware? They don't care about it. They just rely upon these libraries.
Right. And not only that, and the goal is that the CRT libraries are used across all the services that are provided by AWS. So AWS itself internally, they want to have a common set of libraries for all their services so that each service doesn't need to pick a different version of the OpenSSL implementation or a checksum implementation. So they are the same set of libraries, and they expect or recommend customers to use the same so that it's all easy to support and manage and provide good performance on the AWS hardware.
Which is again a very classic AWS mentality, because essentially you're using you creating the libraries that can be used by your services, and then you're exposing them to the customer as well. So in AWS language, the blast radius is fairly big. If we optimize these libraries, we are actually optimizing a whole bunch of services, and then of course the customer experience too.
Exactly. So
Yep.
each service doesn't need to worry about optimizing, or is there a version of the Open SSL that we need to pick, and are there new security patches they need to port and things like that. So these are all done by the common library set of folks, and everybody can leverage these.
Got it. Fantastic. Okay, so what do we have to show today?
Okay, so let's jump right into this. So Badri, take it away. It's all yours.
Yeah, so the first, like Ravi mentioned earlier, some of these, the libraries, the one that most heavily used library is called AWS LC, provides all the crypto services. There is AES GCM implementation and then AES XTS implementation. AES basically means advanced services, right? So GCM is Galio's counter method. So this is one of the most commonly used algorithm for authentication as well as the encryption. And like Ravi mentioned, pretty much all services use this. And one of the things that was how optimized is AES GC implementation on the Intel hardware. Is it actually using the latest and greatest ISR that Intel provides as part of the third and fourth generation hardware, Xeon hardware. So one thing noticed was that it was not using the latest AVX 512 instructions. It was still using old AES and I instructions. So we went and optimized both the GCM, both encryption side as well as the decryption side of the algorithm to make use of the AVX 512 and then the vectored VPC mul instructions. So as you can see across the board at all buffer sizes or the block sizes, we get anywhere performance from 1x to 2.1x performance by using purely just switching the implementation from the NI instructions to the AVX 512 instructions.
Yeah, and just to kind of highlight how big a deal this is, right? This is measured on M7i with and without the optimization. If you compare it to M6i or if you compare it to M5, it will be a significant boost because M7i on its own delivers a lot of performance improvement. We saw that in the last session that we did with Yaron. And so this is optimization of this on M7i itself, right? And also, as Badri mentioned, this is transparent to anyone that is using the AWS libcrypto or the AWS LC. So any service in AWS or any customer that might be using AWS LC just gets this benefit.
So by default, if you're using an AWS service that is using some crypto mechanism, you will see these performance improvements automatically without doing anything at all.
That's right.
Exactly. So all these changes were already integrated into AWS LC library, and you are using the latest version of the library. Depending on what hardware you are using, it will automatically select the implementation that is optimal for that particular hardware. If you are using 10-year-old hardware, then it will switch back to the older implementation. But if you are using anything like C6 or M6 or M7, it would automatically start using the 512 instructions.
And I guess that's the purpose of CRT, as you explained earlier, because it hides away those complexities. You don't have to worry about it. It'll pick the right version automatically based upon the underlying hardware where your application is deployed.
Correct.
Yep.
Now, usually, I see this is about a 2 to 2.5 times improvement in that element of the entire application stack. Yes, 2 to 2.5 times improvement is really good, but of the entire stack, how much compute power is really utilized by crypto, for example? Is it like 5%, 10%, 20%?
So this is dependent on the applications. If an application is spending a lot of time dealing with encrypted connections, for example, this can be substantial. So if you're using something like Nginx and you're using it as a reverse proxy, if you're using it as a web server that is a gateway, you're going to be dealing with encrypted connections most of the time, millions of incoming connections. In those scenarios, you'll probably see almost the performance improvement that this kind of single function measurement is doing, right? So you're expecting to see an order of magnitude improvement. If it's something like, say, you're doing a WordPress site that's being hosted, right, or something equivalent to that, where there are lots of incoming connections, all of them are encrypted, but you're also, serving some data. There is some access to databases and a few other operations happening. There, it's probably something like 30 to 40% improvement just from this. So what is 2x here will translate to 30 to 40% because that's the amount of time that your application is spending dealing with those. So it's a matter of how much time the application is spending, and that is something that you can assess very well. And one of the follow-up talks that Arun will host will have a session on how you can profile your application and understand how much time is spent on things like what does perf record show for say libcrypto footprint in your application and so on.
Wonderful. So the recommendation really here is to use the CRT and use it on the latest hardware. But even if you're using the older hardware, it'll pick the right version for you. Absolutely nothing the customer has to do anything out of the box.
That's right.
Okay.
And and similarly, this is AES XDS. So Badri, do you want to talk to this?
Yes. So the other one which we optimize is called AES XDS, which stands for the the tweakable block cipher, which is heavily used in actually storing the data on the disk, whereas AES GCM is heavily used for the in-flight connections for the encrypting and the decrypting, whereas AES XPS is optimized for the storage on the rest. And again, we looked at implementation. We optimized for the M6 and M7 instances using AVX512. Again, we saw the improvement between about 1.2, I guess, 2.1x performance improvement across the board. Again, all these changes are already accepted into AWS LC, which is available for the customer to use right away.
So
So
GCM was in flight, XTS is storage at rest.
correct. That's exactly right. So if you think about things like services in AWS that are probably dealing with connections in flight, the Elastic Load Balancer, the web application firewall, the API gateway, all of these we would expect would benefit significantly when they adopt m7i with these kind of optimizations that are in LC. And for XTS, it's any services or any customer that uses it for reading and writing encrypted data to storage.
So what services would be relevant in that space, like S3?
Yeah, and that's a good segue, I think, to the next one. And I'll give a little bit of context here because it'll help explain the impact. So the data on the left is from a talk that Andy Warfield, who's a AWS VP and distinguished engineer, gave earlier this year in the Fast 23 conference. What that is showing is that for a customer that has a bucket size of 3.7 petabytes and needs a peak throughput of 2.3 megabyte request per second, 2.3 million, sorry, requests per second. The capacity requirement of 3.7 petabytes can be satisfied with 143 hard disks. But to satisfy the IOPS requirement of 2.3 million requests per second, you need 19,000 hard disks. Right? So that's a staggering difference. But the way S3 works, there are hundreds and thousands of customers that end up having their data spread across more than 1 million drives. So the kind of IOPS that they can get, right, because of the scale that S3 operates at is staggering. But to achieve that, AWS themselves and S3 in particular has a lot of overheads. For example, the checksum computations that they need to do. Right. So because data is, every put is spread out as many disks as possible, that data has to be checked for consistency whenever it is sharded out, when it's requested, and so on. So that is where the checksum computation need comes from. And this data is showing how much of a throughput improvement has been done with the optimization that we have submitted. So we expect this to be merged soon as well. But do you want to speak to this one?
Yeah. So right now the S3 is actually using ERC32C algorithm, which is again not optimized for AV quite well implementation optimization progress. But as you can see, we see the improvement across the board anywhere from again 1x to 1 to I guess almost 3.5x. This work is not merged yet. It's still under currently review because again, since S3 is heavily used, we want to make sure that we get it right. And just in the AWS checksum team is also closely looking at the implementation so that we don't mess up. So.
Yeah, so I mean, something, for a service that operates at this scale, even a 1 to 2% optimization matters a lot.
Massive.
Because it's at such a large scale. And when you look at 4 billion checksum computations, and you're talking about going up to 3.3x throughput improvement, that is a huge impact. Right?
That's massive.
This is, there are two ways to think about this. One is, when you are operating at a hyperscale like AWS is, you get access to the kind of performance in terms of this IOPS example here that you really cannot in any other scenario, just because of the sheer scale. But at the same time, what we are doing is making sure that the optimization that we do amplify that impact so that it has, to your point, a much broader blast radius, and it benefits AWS and the customers.
Right. And having worked at Amazon, I completely understand that philosophy because they just squeeze the juice out of, at that scale, you're right. Even 1% improvement is a massive improvement. And here we're seeing up to 3.3. One question I have though is who defines the buffer size? Is this the application? Is it automatically picked up? How do you know that what kind of improvement are you getting here?
Yeah, I mean, there's a few variables that control that. It depends on what was the size of the data that you were writing into S3 and the checksum that needed to be calculated on that. There's a few other variables that define it, which is why there is a spread here that we've done in terms of calculating the performance improvement that you see at different buffer sizes. So well, I guess it really depends on the particular use case to say what buffer sizes are the most common. For something that is as widespread as S3, I would expect that they will see almost every buffer size being used.
No, that's a fair point. And so what you're showing here is no matter what the buffer size you use, you will see at least a 1x improvement, which is double basically, and then up to 3 times essentially. So that's an order of a magnitude.
Yeah, so the least you'll see is about, I think it was 1.4x, so which is 40% faster, and the highest you will see with the 16K buffer size is 3.3x, right? So it's,
Yeah.
and the average is somewhere in between the two.
Beautiful. Okay, well, so we talked about GCM, XDS, checksum. What else we got?
Okay, so a lot of people might have a question about, okay, all of this is things that we're doing AWS and for some of the AWS services, customers do use those, but what about the broader ecosystem? So it's something that I wanted to highlight, that there's existing Intel implementations. There is a combination of, if you pick up QAT Engine, and these are all open source and have been from the beginning. If you pick up QAT Engine, as I mentioned earlier, there are also additional software innovations that are incorporated, so you get even higher throughput. You can think of all the work that we were showing so far as a quote-unquote single buffer implementation. The QAT engine has a multi-buffer implementation, so you can do go up to 8x throughput improvement on some of these that we are showing. We're at 2x right now, right? And the QAT engine in turn uses additional underlying libraries like IPP Crypto and ISIL. So all of the IPP is the Intel Performance Primitives. ISIL is the Intel Storage Acceleration Library, and these are well-maintained open source libraries that have had a strong history of contributions on an ongoing basis. But besides these, right, these are relevant because if you're using, say, OpenSSL 1.1.1, which is the most common still with most operating system distros, this is a pluggable engine that works with OpenSSL. So you just compile or just download these, and you have the benefit of all of these. If you're willing to go to the latest generation of OpenSSL, the 3.1, those 3 algorithms that we talked about have been upstreamed into OpenSSL, and as we mentioned earlier, OpenJDK has it, and Boring SSL as well. So it's available to the broader ecosystem. There are a couple of additional steps you would need to take, like downloading the QAT engine and the other libraries and making sure OpenSSL is using them, but the benefits are well worth it. And besides that, we also have additional work planned for many other CRT, many other common runtime libraries that AWS has, both on the encryption side of it, but as well as other things like compression.
That's wonderful, actually. So we have done significant improvements in encryption, both in flight and at rest, and checksum. Those are the 3 we talked about. Customers don't have to do anything about it. If they're using the CRT, they automatically get all those benefits. A lot of the AWS services get benefit out of that. And as Amazon says, this is day one. We're just getting started. There are a lot more optimizations to come, and these are the places that you have said it. Take a look at this. Any other closing comments that you want to make here?
I think it would be great if people are trying it out. Let us know what you see. Let us know if you face issues and what else you would like to see.
Yeah, we truly want to keep the customer obsession in there. So try this out. See what else would you like to do. We want to hear from you, and that helps us prioritize what you want to work on. Badri, any closing comment from you? Badri, any closing comment from you?
Yeah, I think I echo what Ravi said. So we handpicked some of these libraries to optimize. If the customers are interested in other set of libraries, not in our priority list, feel free to let us know. We'll definitely take a look at it and say, okay, well, we'll optimize those for them, right? So we are in the business of optimizing the libraries for the end customer. We just want to make sure that the end customer is happy on our Intel hardware.
Perfect. Thank you very much. This is fantastic. So again, the recommendation to customers is really use the 7th generation of Intel instances on AWS. Use the common runtime libraries, use the latest upstream software that is already available in downstream, and that gives you the most bang for your buck, essentially.
Yep.
Fantastic. Thank you, everybody. Hope you had fun, and we'll be back with another episode soon. Bye.
Okay. Thank you. Bye.
Okay, thank you.